So here's the problem. We've got a function u which is harmonic in a domain omega, and we let g of z be partial derivative of u with respect to x at xy minus I times partial derivative with respect to y of u of xy. We have to show that g is a holomorphic function. Then we ask, if f is a holomorphic function whose derivative is g, what sort of relation is there between f and u? Well, let's start out. How do we show that g is a holomorphic function? Well, we can write g of z is equal to, well, we've already got a u, so let's avoid u and v. Let's try once again r of xy plus I times s of xy. That's where z is equal to x plus iy in omega. And let's see what we can see about the Cauchy-Riemann equations for g. So we have to work out r sub x, r sub y, s sub x, and s sub y. Well, actually r is equal to u sub x, so r sub x is uxx. R is equal to u sub x, so r sub y is uxy. S sub x, well, s is equal to minus u sub y, so s sub x is minus uyx, and s sub y in much the same way is uyy. So what can we say about these things? Do the Cauchy-Riemann equations hold? Well, u is harmonic, tells us that uxx plus uyy is equal to 0. In other words, uxx is equal to minus uyy. In other words, this is equal to that. And the other thing is that when u is harmonic, then we're always assuming that all these partial derivatives exist and are continuous and so on, and that means that uxy is equal to uyx. Doesn't matter which order we do the partial derivatives in, and that tells us that r sub y is equal to minus s sub x. So we've just seen that the Cauchy-Riemann equations hold for g. And that means that g is holomorphic. Now, to be precise, actually, we should know that all of these things, all of these partial derivatives are continuous, but that's actually part of the assumption of u being harmonic, so there's no problem with that. Now, if f is in h of omega and f prime is equal to g, what can we say about f and u? Well, if f is holomorphic, then we can write f also in terms of a real part and an imaginary part, and we're running out of letters at this point, but let me say, let's write f of z is equal to pxy plus I times q of xy. Now, according to the Cauchy-Riemann equations, when we write down f prime of z is equal to g of z, that means that g of z is equal to pxy, but with a partial derivative with respect to x, plus I times q, partial derivative with respect to x at xy, which is the same thing as px xy minus I times py xy, because the Cauchy-Riemann equations hold for p and q, so qx is equal to minus py. Now, there's something that we can say about this, and we can compare that to that, or we can compare that to, in fact, r of xy is equal to, it's ux, and s of xy is equal to minus u sub y. So this is also the same thing as u sub x, xy, minus I times u sub y of xy. Now, these things are the same. That means that equating the real parts and the imaginary parts, that says that px is equal to ux and p sub y is equal to u sub y. Okay, so if I look now at the function u minus p, I could also look at u minus p, x is equal to 0, u minus p, y is equal to 0, u minus p is equal to a constant. That's to say that, in conclusion, that u is equal to the real part of f plus some constant. And, by the way, that means that the harmonic conjugate for v can be found as the imaginary part of f. And that's the end of that one.